So now we're going to talk about buffer capacity. The pH of a buffered solution is determined by the ratio of our base to our acid, or the A negative, the conjugate base, over the concentration of the original acid, molecular form. As long as this doesn't change much, the pH won't change much. The more concentrated these two are, the more hydronium and hydroxide the solution will be able to absorb. So if you think about a sponge can only absorb so much before it reaches capacity. Same with a buffered solution. So the larger the concentrations, the bigger the buffer capacity. If I have my bar graphs from up above, if I have my buffered solution and we're at a smaller concentration versus, let's say that we have our initial starting point where I have a larger initial concentration, I have a bigger buffer capacity. So if we think about it, how much can be added to a system that's been buffered before I overcapacitate it? So if we go back to that sponge example, the sponge eventually fills. If I'm pouring in a strong acid or a strong base to a buffered solution, it has a certain capacity. A certain amount of acid or base can be absorbed before the pH begins to swing. But I can overcapacitate it if I pour in too much. Just as the sponge can hold a certain amount of water, a buffered solution has a certain capacity before pHs go out of whack. So as long as this doesn't change much, the pH won't change much. That ratio of negative A of the base over the acid, and we look at that, and the more concentrated these two are, the more hydrogen ion and hydroxide ion the solution will be able to absorb. Obviously, again, my bar graph, I have much larger capacity the more concentrated the buffer solution is, if this is my starting point, compared to this. When we're looking at pH ranges, the pH range in which the buffer acts effectively is in limit resistant change in either direction when we have the concentration of our acid equal to the concentration of the A negative or X negative, whatever that base is. If we think about that, we're looking at, let's say, our bar graph again. If we have concentrations of both of them versus if we have concentration of one that's much smaller, it wouldn't make so much sense because this one would be consumed so much quicker than the other one. So this would be the optimal pH range. It wouldn't make sense to make a buffering solution where I have a small amount of the one partner compared to the other. So what we're saying is an optimal pH range is one where we begin with the buffering capacity of equal amounts. We can also say that the optimal pH of a buffer is when our pH is equal to pKa. And if we think back to an earlier equation, when we said that H plus is equal to Ka times acid over our base, and we said that when these two equal each other, they would cancel out. So then we have Ka equal to H, or pH equal to pKa. So let's think about this. What is the optimal pH buffered by a solution containing acetic acid and sodium acetate? Now, we want to be sure that whenever we look at buffering systems, that the pH that we find is plus or minus 1 pH unit. Okay, so we're given the Ka for acetic acid, and when we are making this buffering solution, remember we want the pH equal to the pKa. So we're told the Ka is 1.8 times 10 to the negative 5. So let's find the pKa, which would be the negative log of 1.8 times 10 to the negative 5, because that will be equal to the pH that we want. And so let's plug that into our calculator. The negative log of 1.8 times 10 to the negative 5, and we get 4.74. So the pH range of this buffer system is 4.74 plus or minus 1 unit. So when we add a strong acid or a strong base, first we need to do the stoichiometry. A strong base will grab protons from the weak acid, which will reduce the concentration of that acid. A strong acid will add its proton to the anion of the salt, reducing that base. So to do the equilibrium problem, it's most easily done with that Henderson-Hasselbalch equation. Let's look at an example. Actually, first I'm going to draw a little diagram. You don't need to draw this, or maybe you want to draw this in a margin or on a separate piece of scrap paper, but I just kind of want to show you a little visual here. Let's say that this is my buffered system. And it contains my weak acid and its conjugate base, X negative. We also, maybe we call this HA and A negative, doesn't matter. But we have possibility here of adding a strong acid. All right, so we add a strong acid to our buffered system, and we get that strong acid that 100% dissociates. We get X or H plus, and it is reacting, that acid's H plus is reacting with the base in our buffered system to create more acid. Now I got to remember if I'm using A's or X's. So we have the strong acid, the hydronium from the acid, plus the X from our buffered system. It's going to produce more acid. So if I add a strong acid, I produce more acid. Now let's look at if I add a strong base. Hydroxide. So if I have hydroxide, hydroxide obviously wants to react with the acid. And what is that going to produce? Well, we've got hydroxide grabbing the proton, so H2O. And what does that leave us with? X minus. So when I add a strong base, it produces more base. We then need to recalculate the concentration of HX and X minus. And once we recalculate that, then we can solve for the pH. So hopefully this flow chart helps you to see that I'm starting with the known amounts of buffered system, and I'm adding either a strong acid or a strong base to create more of either my acid or my base. Then we need to recalculate so we can solve for the pH. So in this example, a buffer is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate. And again, we know that this is our conjugate base. So then we make enough to have a 1 liter solution. Calculate the pH of the solution after 0.2 moles of a strong base sodium hydroxide is added. So let's look at what we have. We have hydroxide, and we know that adding a strong base, that hydroxide is going to react with the acid. So we're going to take that hydroxide plus our acetic acid, which is HC2H3O2. And we know that this is going to make H2O and acetate. Okay, now let's look at what we had before this reaction happened. So we were told we were given 0.2 moles, which we know is in 1 liter solution, so 0.2 molar. Our acid actually, as I'm looking at this, and I happen to skip down here, we have a little typo. This should be 0.02 moles because we do the same problem with 0.2 down here. So we're making this 0.02. Our acetic acid is 0.3 molar, and our acetate is 0.3 molar. Now, we know that as this reaction is happening, it's all a 1-to-1 ratio. We're going to use up this hydroxide, right? We know that this reaction is going to create more acetate. And what are we going to use up first? Obviously the 0.02 over the 0.3. So after this reaction, we're going to lose 0.02. So use up that hydroxide, which is going to consume acid, and it's going to produce that same amount of acetate. So we have 0.3 minus 0.02 to give us 0.28 molar acid, 0.3 plus 0.02, 0.32 of the base. And now what we need to do is plug it into our Henderson-Hasselbalch equation, where we have pH is equal to the negative log of the Ka of acetic acid. And we're just going to look up the acetic acid on my appendix D. Acetic acid is 1.8 times 10 to the negative 5. Plus the log of my base, 0.32, over my acid, 0.28. Now let's plug that in to my calculator. So I have the negative log of 1.8 times 10 to the negative 5, which we should notice is the same as the pH of the buffer that they gave to us, plus the log of 0.32 divided by 0.28. And we should get a pH of 4.80. And we can also see that adding that strong base only rose the pH by what, 0.06 pH units. So yes, it made it more basic, but not by very much. Now for comparison, we're going to calculate the pH that would result in 0.2. So going back to what I originally thought that it said, of NaOH was added to 1 liter of pure water. So we're let's set it up. We'll just use the same equation. And our before for the OH is going to be 0.2 molar. Same 0.3 molar for the acetic acid and 0.3 molar for the acetate. But then obviously we would use up the hydroxide first, so we're going to subtract 0.2, consume that, and produce more acetate. So what am I left with? 0.3 minus 0.2 is 0.1 molar of my acid, 0.5 molar of my acetate. So to plug it into here again, my pH is the negative log of 1.8 times 10 to the negative 5 plus the log of, remember my base, 0.5 over 0.1. And let's do that problem here. The negative log of 1.8 times 10 to the negative 5th plus the log of 0.5 divided by 0.1. We get a pH value of 5.44 units. And if we look, the pH of the buffer is 4.74. And up here, remember, that will give us the usable pH range of plus or minus 1 pH unit of pKa. And we know our pKa for this was 4.74. So when we say plus or minus, we were within that 1 pH unit. But notice we had a substantially more concentrated sodium hydroxide, 0.2 as opposed to 0.02. And so yes, it did raise the pH, make it more basic, but not by that much. Let's look to see what happens now when we add an acid. So we're going to take that original buffer, but we're going to add 0.02 moles of HCl. And again, we're assuming it's in a 1 liter solution. So we have our, looking back at our chart here, we have our buffered system. Now we're going to, instead, last time we added the strong base and we made more base. This time we were going to add acid. We're going to create more acid. So let's write down we know that HCl is going to 100% dissociate. So we're going to forget about our spectator ion, our chloride, but we're going to have H+. And we know that that is going to react with our conjugate base from up above, our acetate, our C2H3O2 minus. And that's going to make more acid, our C2H3O2. Okay, so let's look at what we know that we started with before. I started with 0.02 molar of our H plus, 0.02. How much of the acetate did we start with? We started with 0.3 moles of the sodium acetate, of the acetate. So 0.3. And we also started with 0.3 of the acid. And we are all a 1:1:1 ratio, so we're going to consume our H plus first. So minus 0.02, and we'll consume our acetate, minus 0.02, which means we'll produce plus 0.02 for our acid. Now this gives us 0.28, and this gives us 0.32. So, and then of course 0. So we'll plug this into our Henderson-Hasselbalch equation. pH equals negative log of 1.8 times 10 to the negative 5 plus the log of our base over our acid. Our base is our 0.28. Our acid that's right here is 0.32. And let's see what we get here. The negative log of 1.8 times 10 to the negative 5th plus the log of 0.28 divided by 0.32. and we get 4.69. So pH is equal to 4.69 pH units. And if we think about it, we started at 4.74 was the pH of the buffer. We added a strong acid. So it went down, which would make sense. To become more acidic would be lowering in the pH, 4.74 down to 4.69 is lowering. Now if we compare this, if we were to add that same amount of HCl to pure water, again, we know that this 100% dissociates, and so we would take, to find the pH of that, is just the negative log of its concentration, because this would totally dissociate, and this would be our H+. So negative log of 0.02, and that would give us negative log of 0.02, 1.70. So if we took that same amount of HCl and put it in pure water, it would have a pH of 1.70. Taking that same amount of HCl and putting it into a buffered solution only changes the pH. It's just a little bit, giving it a pH of 4.69. Buffer solutions are conjugate pairs that act as a sponge, soaking up excess acid or excess base, preventing a shift in pH. It changes slightly, but certainly not to the degree of it if it was in pure water by itself.